All right, so the next type of limits we're going to find are limits of piecewise functions, which we kind of saw graphically with all those different sections of graph, but now we're going to look at it more numerically. A piecewise function is literally a function defined in different pieces. We have used these with our Desmos stuff before, where we've restricted domains. So that's really what we're looking at. So for each separate domain, we're told which piece of the function to use. So we're going to start by just finding some values in our piecewise function. So first off, if I have this piecewise function, you can see our three different pieces and our three different domains. I'd like to start with f of 2. So we need to decide which domain applies when x is 2. And that would be our biggest piece there, which is the domain from x greater than 1. So all I'm going to do is plug this value into that corresponding piece. So it's literally just going to be 6 times 2 minus 1, which is 11. Okay, so f of 2 is 11. So don't plug it into each piece, only plug it in with the corresponding domain or the corresponding inequality. How about f of 1? So now we can see the middle piece applies from -5 less than equal to 1. The biggest piece is x bigger than 1. Obviously, 1 is equal to 1. So we're only going to plug it into that middle one. So x squared, let's put in our 1. 1 squared plus 4. So f of 1 should be 5. Okay, and then now let's go to a limit. So limit's pretty similar. We're still going to pick out which pieces we are, but we'll see something different here in just a sec. So I would like to find the limit as x approaches 0. So first we need to decide which piece applies to 0. Where does 0 live? In which inequality? Looks like it lives pretty comfortably between -5 and 1. So all I'm going to do is take my 0 and substitute it into that middle piece again. Okay, so our first decision is what piece does it work in? And that would just be that middle piece. What about one-sided limits? I would like to find the limit as x approaches 1 from just the right side. Now 1 is actually in two separate pieces. And remember, for a limit, I don't care which one it's actually equal to. I'm looking to see what happens on left and right side. So technically, this middle piece would be the left side of 1 because it's smaller than 1. The bottom piece would be the right side of 1, so that's bigger than 1. So if I just want the right side, I'm just going to put it in that bottom section of the function. Okay, so I don't care about where it's equal. I'm just thinking about what side I'm using. I'm using the right side. So just 6 times 1 minus 1, and I would get a limit of 5. Okay, how about moving on to x approaching -5? Now, -5, if you look at your inequalities, is both a part of the first piece, the first inequality, and the second, So again, we have to think about sides. The first piece would represent the left side. The second piece would represent the right side. And if I'm doing a two-sided limit, a normal guy, I need to think about both. So if your value lives in two different inequalities, we really need to check in both inequalities or in both pieces of our function. Okay, so I'm just going to label this. The left side would be -5 plus 1, which is -4. The right side would be the middle section, which is -5 squared plus 4, which would be 29. So what would you say about your limit if the left side is approaching -4 and the right side is approaching 29? And hopefully you would agree with me that this limit does not exist. Okay, if we're going to plug a piece or a value into two different functions, into two different pieces of the function, they need to come out with that same y value if that's going to be their limit. So let's look at the limit as x approaches 1. Again, 1 is in two different inequalities. We've done this before with just the right side, but because this is my two-sided limit, I have to think about my left side and my right side. Okay, so the left side of 1 would be my middle section, 1 squared plus 4, which is 5. My right side would be the biggest section, which, again, we already found. I'm going to rewrite it. So 6 times 1 minus 1 equals 5. So can you now see that the left side and the right side are approaching that same value of 5? And therefore, my limit would be 5. Okay, so hopefully you can see the difference in the two. You only have to plug it into multiple sections if it's actually part of that domain where it's switching from one piece to another. So that's your piecewise function. Okay, so now let's finish up with 3 conditions in which a limit does not exist. We've already seen 2 of them, and that's when our left side limit does not equal the right side limit. We just saw that with our piecewise. Okay, so just to draw an illustration of that, could be something like, here's my graph. I think we saw this earlier with, I had a function coming in like this, and then it came out just like that, right? So limit, or left side value does not equal the right side value, therefore this limit does not exist. The second type of function that we could consider a limit does not exist is when your limit is either positive or negative infinity. So technically, because positive and negative infinity aren't a numerical value, we can say that limit does not exist. I would say, though, if you have a function in which both sides are approaching positive infinity, go ahead and say positive infinity. Okay? Or if both sides are approaching negative infinity, go ahead and say negative infinity. Technically, though, we could say that limit does not exist. The last type of function that we would say a limit does not exist is what's called an oscillating function. Oops, I'm not going to say oscillating. When it oscillates. If you think about an oscillating fan, it's those fans that go back and forth. You can make it turn. Functions can do that too, where they never really settle on a value. So I have one on a graph here that I want to show you. This is the equation, sine of 1 over x, that I have graphed. And when you graph, from here, it looks like it's settling in right around 0. But look what happens when I zoom in. So I'm going to zoom in. Okay, a lot more is going on there than you would originally think. Okay, so it looks like it drops down, and then I would think it connects back up, right? I'm going to zoom in again. Look what happens as we get closer. It just keeps going back and forth more and more and more. It's never going to settle down at one specific value, and we can't get close enough, even if it did settle, to see what it is. So this is an example of an oscillating function. Okay, so just to draw something in here, it would be like, and then it comes right back out. Okay, so those are 3 specific examples when a limit does not exist.